In this class we will explain about register transfer logic and how this can be used for designing very large digital systems. First we can recap what is a digital system. Digital system is an interconnection of hardware modules that do a certain task on the information. Registers plus operations performed on the data stored in them, that will form a digital module. Modules are interconnected with common data and control paths to form a digital computer system. The interconnection of digital functions to form a digital system module cannot be described by means of combinational or sequential logic techniques. These techniques were developed to describe a digital system at the gate and flip-flop level. So, in the case of very large systems that may contain a number of modules and we have to interconnect that modules, then in that case it will be difficult and complicated if you are using the if you are designing at a gate and flip-flop level, or if you are using combinational or sequential logic techniques for describing that circuit. Not suitable for describing the system at the digital function level. Then to describe a digital system in terms of functions such as adder, decoder, registers, it is necessary to employ a high level mathematical notation. Just like our programming language, the register transfer logic fulfills this requirement. In the case of register transfer logic, registers are selected to be the primitive components in the digital system instead of flip-flops or gate, rather than the gate and flip-flop as in the sequential logic. Then it is possible to describe in a concise and precise manner the information flow and processing task among the data stored in the registers. And the register transfer logic uses a set of expressions and statements which resemble the statements used in our programming languages. So it will be easy to describe our digital system. This notation provides the necessary tools for specifying a specific set of interconnections between various digital functions, closely related to the way people would prefer to specify the operations of a digital system. Next we can explain the different components of RTL. Registers, binary information, microoperation and control functions. These are the major components of the RTL. Register defined in the register transfer logic notation encompasses all registers such as shift register, counter, memory units, etc. This is not simply registers, this is a general term for all these things. Another component is binary information. Binary information stored in registers may be binary number, binary coded decimal number, alphanumeric character, control information, or any other binary coded information. Another component is microoperation. The operations performed on the data stored in registers, that will form the micro operation, an elementary operation that can be performed in parallel during one clock pulse period. The result of the operation may replace the previous binary information of a register or may be transferred to another register. And examples for microoperations are shift, count, add, clear, load, etc. Another component is control function. Control function will initiate the sequence of microoperations. We can control a statement or operation by using the control function. A binary variable, this is actually a binary variable that when in one binary state initiates an operation and when in other binary state inhibits the operation. That is, when it is 0, that will do some operation, and for example if that value is 1, that will initiate the microoperation, and if it is 0, that will inhibit the operation. We can explain different types of microoperations. We can have inter-register transfer, arithmetic microoperation, logic microoperation, and shift microoperation. First, we can consider the inter-register transfer. Computer registers are designated by capital letters. In the case of our register transfer logic, we will use capital letters, sometimes followed by numerals, to denote the function of registers. For example, R1, MAR, PC, IR, SR. R1 a process register, MAR memory address register, program counter, instruction register, status register. So we can use names like this. This convention will be used in register transfer logic. Individual flip-flops in an n-bit register are numbered in sequence from 0 to n-1. For example, a register can be represented just like this, or showing the individual bits 0, 1 to up to 7, or like this. We can express like this, 0 to 15, then name of the register. Then we can partition our register into different parts. For example, 0 to 7, we have a 16-bit register, and we have divided that register into two halves, lower half and upper half. Assume that the entire name of the register is PC, so we can divide this register into PC low and PC high, like this also. So we can represent our registers in different ways in our register transfer logic. The main advantage of this register transfer logic is that it is just like a programming language statement, and different vendors have different register transfer languages. So if you write or if you explain a digital system in this register transfer language, then we can that will be very easy, because these statements will be just like programming language or our English like languages. So we can easily specify digital systems. Then these digital systems can these specifications or this register transfer language specification can be compiled by using special compilers that will translate these high level statements into flip-flop or gate level, or we can say that resistor transfer level circuits. And that file can be given into a fabrication lab, and we can easily fabricate our digital system or ICs. That is, we can write our or specify our digital system in very high level language, that is in register transfer logic. Then that can be translated into low level circuit, that is at the resistor or transistor level circuit, with the help of some compiler, special compilers. And that object file or the resistor transistor level file can be given into a fabrication lab, and then we can fabricate our ICs. That is the advantage of this register transfer logic or register transfer language. Okay, registers can be specified in a register transfer language with declaration statements. For example, declare register A8, MBR 12, PC 16. This will actually create registers, a register with the name A and 8 bits, another register with the name MBR with 12 bits, another register PC with 16 bit. Then we can create sub-registers by using declare sub-register statement. For example, declare sub-register PC low is equal to PC 1 to 8. We already, before that we have to declare this PC. So PC 1 to 8, this bits 1 to 8. Then PC H means PC high byte, that is equal to PC 9 to 16. From this register, the bits from 9 to 16 will form our sub register PC high. Okay.